Hey, y'all, let's cover section 7.1, angles and their measures. So it says the definition is draw pictures to help you understand the following terms. Array. Array is a directed line segment. It consists of one point on a line and all points extending in one direction from that point. The first point is called the endpoint. So if we have a line, which just assume this is a line, I'm not going to do the whole, okay, maybe not. I'm just going to do it as a dotted line, even though it's really a line. I just want to show you based on a line. It says a directed line segment that consists of one point on a line. So here's a point on the line and all points extending in one direction from that point. So y'all know I can't draw, but I'm going to do my darndest. So array would be all points from this point forward in this direction to infinity or negative infinity or whichever direction it's heading. But the points behind it are not a part of that ray. All right, a vertex. A vertex is the endpoint. So this whole thing is a ray. We already know this now as an endpoint. And it says a vertex is the endpoint of the angle, and the two rays are the sides of the angle. So I kind of need an angle first because the angle is the union of two rays having a common endpoint. So let's just create another ray. It's on a different line, it has to be. And we've got another ray that shares the same endpoint as the original ray. And this is a ray as well. And angle is the space in between these two rays, not at the endpoint, of course. And this is the angle, and I'm just going to label that as theta. That it's usually a Greek letter. In this case, I'm going to use theta, and that's typically what you'll see me using. The other thing to know is where these two rays share that endpoint, it's not just an endpoint anymore. It is the vertex of this angle. So that little guy who was an endpoint for both of those is now the vertex of angle theta. Okay. Greek letters are often used as variables for the measure of an angle. And just to get you comfortable with some of the ones you'll see me using, I have other ones I'll be using as well, just for giggles. Greek letter, this would be theta. You'll see me use theta a lot. Phi or phi, pho, phum, who knows. Alpha, beta, gamma. You'll see me using omega. You'll see me using mu. So we'll just use a few different ones just to get you acclimated to where we're not just using X's and Y's on things, because typically angles are measured with Greek letters. All right, initial side, a fixed ray, and rotate the other. The terminal side is the rotated ray. Okay, so for this one, if we think of a fixed array, or fixed ray means a ray that cannot pivot or move or do anything. It is just fixed, which means it cannot move from its original position. All right, and this fixed ray is considered the initial side of the angle. Initial side of the angle. And assume there's another ray on top of it, exactly on top of it, showing the same endpoint, heading the same direction, but this one's not fixed. This one can rotate. And this is going to be the terminal side of the angle. And assume that it's being rotated from this initial side. And we're going to go counterclockwise. And let's just assume that our angle or our terminal side ends here. And this is known as the terminal side. And that is because that is the end. So when we terminate something, we end something, or think relationships, think lives. Terminal just means the ending. So that's the ending side for this angle. And again, I'm going to name this guy theta, just to get us comfortable with it. All right. So measure of angle is the amount of rotation from the initial side to the terminal side. And that would be what this theta is. It's the measure of the angle. All right, let's talk about degree. If I were to ask you how many degrees are in a circle, you're going to tell me 360 degrees, and you'd be right. But you've got to understand that there are 360 degrees around this circle. So to find 1 degree, that is 1 over 360 of a circular rotation. So a degree is 1/360th. Standard position. Standard position is, if you think of a Cartesian coordinate system, the XY graph, and you know I can't draw straight lines, y'all, so bear with me. So we've got an X and we've got a Y. I haven't changed that, still the same. Let's just assume that our vertex of our angle, which is this guy right here, our vertex of our angle is on the origin at 0, 0. And the initial side of that angle extends along the positive x-axis. So it will always shoot off to the positive version of the x-axis, not ever the negative. So there's our vertex. And here is our standard initial side. And you'll see me using this a lot. This is called standard position. Now we can move the other terminal side that we assume is sitting on top of this. It can be moved around. Currently, we've only talked about going counterclockwise on this system. So let's talk about a right angle. To draw a 90-degree angle, we have to calculate 90 divided by 360. And that's going to be 1/4 around the entire assuming circle. All right, so, well, this would be 1, 2, 3, 4. So they would have to go off this way. And this would be our terminal side. And our angle, I'm not going to label it theta. I'm going to label it 90 degrees. Okay. Counterclockwise from the positive x-axis. So again, we assumed that our now terminal side started off on our initial side and rotated straight up into a perpendicular, which is 90 degrees. All right, let's draw a straight angle using the same XY coordinate system. We've got our initial standard position, which is our vertex at the center, and our initial side is always along the x-axis, the positive x-axis. To create a straight angle, which is 180 degrees, half of a circle, we have to take 180 divided by 360, and we get that 1/2, which means we're only going halfway around. So again, assume that you've got another ray sitting on top of where the vertex is this way, and we're going to rotate it all the way around towards the negative side. So what we just did was drawing this piece, which started off over here, and then we rotated it 180 degrees, which makes up half of a circle. Okay, it's half of a rotation of a circle. My goodness, my nose is bothering me. All right, let's make sure there's nothing else I wanted to tell you. You've got initial side, terminating side, terminal side. Same thing here. This is our initial side. This is our angle. And this is our terminal side. Terminal side. All right, the pink is our terminal side. So let's go to the next page. All right, positive angles. So when the angle is measured counterclockwise, which is the only thing we've done up to this point, from the initial side, our positive x-axis, then that's going to create a positive angle. So if we have our x's and y's, and we've got our vertex here at the origin, standard position, the initial ray, it's our initial side, does not move. And when we measure counterclockwise, so in this direction, that is going to create a positive angle. It creates a positive angle. So when moving in this direction from the initial side, that creates a positive angle. If instead, again, we've got the vertex, and here is our initial side. instead of going counterclockwise, we would go clockwise for it to be a negative angle, because the negative angle, when the angle is measured clockwise from the initial side to the terminal side, I guess I need to create a terminal side for you so that you can see that this creates a positive. And this one, let's just take it all the way over here for fun, creates a negative angle. All right, so let's just say negative 100 degrees would be going in this direction. This one would be more like a positive 60 degrees. So this way creates a negative angle. All right, quadrantals. Quadrantal angles are angles in the standard position, which means the vertex is at the origin 0, 0, and the initial side is along the positive x-axis. So standard position, whose terminal side lies on axes including 0, 90, 180, 270, and 360 degrees. So we need to see what each of those angles look like. I think we've already seen the 91 and the 180. So I definitely want to do I'll do them all just for fun. All right, so there's the 0. Get you a 90, 0 degrees. We've got a 180 degrees, a 270, and 360. Gonna do a little labeling real quick. All right. So 0 degrees, we start off at the vertex and on the initial side. And that's just going to be for all of them. So for the 0, 0 degrees means it's not changing degrees at all. It's staying exactly where it is. So the angle of 0 degrees is just truly the initial side. Okay. I'm going to go through 90 and 180 relatively fast because we've already done those. So, and I'm going to do the terminal side for each angle. So for 0 degrees, that's going to be the terminal side. Initial and terminal sides are going to be the same. All right. And then for the 90 degrees, the initial side is this one. And then the terminal side is truly 90 degrees from the initial side over. And it is positive, so we're going counterclockwise. I'm just going to get you your final terminal side highlighted. All right. So initial and terminal. And this is 90 degrees. The next one is 180 degrees. We've got our initial side here. And our terminal side is going to be 180 degrees. And we have to go counterclockwise. And that lands over here where our negative x-axis is. So our terminal side is this guy. All right, 270 degrees. For this one, again, initial side, but we're going to go counterclockwise all the way around to our terminal side of 270 degrees. Initial, terminal, and this angle is 270 degrees. This one's 180. This one already designated as 90. All right, and then the last one we have here is 360 degrees. And we've got our initial side drawn. I just need to create my terminal side. So to create a 360 degree angle, I'm going counterclockwise. And I land back where my initial side was. So it's my initial side, and it is my terminal side. Just like the 0 degrees, except for this one went all the way around and came back to visit. Okay. All right, let's draw the following angles. We've got 60 degrees and negative 120 degrees. So for my first one, 60 degrees is right about 30. 60 is right about here. You will not have a protractor or anything fun like that in class. And I won't I won't take points. I just want to make sure that you understand how to draw an angle. And that is 60 degrees. So notice we went counterclockwise because it is a positive angle. So we had to go counterclockwise up to 60 degrees. This one would have been at 90. So it's 2/3 of the way there. And that is my angle. The next one for negative 120 degrees, I have to go south. So my initial side is just like the rest of them have been, my positive x-axis. And negative 120 means instead of going counterclockwise, I have to go clockwise. And that would be 90. So 9, 10, 11, 12, right about here. So right there's my angle of negative 120. And my initial side's the same. I want to make sure present my terminal. There's my terminal side for negative 120. So be careful, make sure with 60, you're going counterclockwise, positive ones, and for negatives, you're going clockwise. All right. Converting between degrees and radians. Central angle, a positive angle whose vertex is at the center of the circle and the rays intersect the circle. Try to get one here. All right. So if you think of our X and Y, you know I can't do this very well, but we say this is a circle. It's not too bad so far, a little bit wonky. So we've got a positive angle whose vertex is at the center of the circle. So there's the vertex, and the rays intersect the circle. So right now these are all rays, and there's more rays as well. There's basically you can look at it as 360 rays. If you want to think of it as 360 degrees. All right, radian, the measure of the central angle of a circle such that the length of the arc between the initial side and the terminal side is equal to the radius of the circle. All right, I'm going to draw real quick for you. See if I can do a decent circle again. Nope, I cannot. Assume that it's a circle. Let's go with it. Need a little stamp. A full revolution, which is 360 degrees. We already know that. So if you start with 0 degrees here and you go all the way around and back, that's 360 degrees. All right, all the way. That's also known as 2 pi. So 2 pi is the radian version. So there's the radians. Anything with a pi symbol is going to be a radian. Anything with a degree symbol, and you could see things that don't have a pi symbol and are still radians. The degrees have to have that cute little dot, that little circle at the top for it to be a degree, or it has to have the word degrees, just to let you know. All right, for a half revolution, 180 degrees, which would be just from here to the negative x-axis, is 180 degrees, but it's also pi. So here it's 180 degrees, but it is also pi radians. So pi is our radians. And 180, because it has the little circle, is our degrees. All right. Find the corresponding radian values for the common measures of the circle. Okay, so I'm going to give these to you, and we're going to go over them again when we get to the unit circle in a couple sections. So for 0 degrees, that would be 0 pi. 30 degrees, let's go with this way, 0 pi, and then if you go all the way back around, it's 2 pi, because that's a full rotation. Half a rotation we now know is just pi, or 180 degrees. So if 90 is half of 180, that means that this has to be half a pi, so that's pi over 2. Pi over 2, pi, so that would be 2 pi over 2. This would be 3 pi over 2. All right, now I'm going to do it based on pi over 6, because 30 degrees is pi over 6, and that means 60 degrees is pi over 3. 120 degrees would be 2 pi over 3. 150 degrees would be 5 pi over 6 pi, and then we'd go to 7 pi over 6, 4 pi over 3, 5 pi over 3, 330 would be 11 pi over 6. All right, I'm going to do my 45s. So pi over 4, because it's half of pi over 2. So then pi over 2, then it would be 3 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4, which is 2 pi. All right, so those are all your radian values for the common measures of a circle. And we'll put that on our unit circle here in just a little bit too. Converting between radians and degrees. 1 revolution we've just spoke about is 2 pi in radians. 180 degrees, half a revolution, is just pi radian. To convert from degrees to radians, you have to multiply by pi over 180. To convert from radians to degrees, you're going to multiply by 180 divided by pi. You're going to want to have this information on your note card, okay? Either use it this way, which is how you usually have me, I usually have to do it in class, or you can use it as the proportion of degrees to 180 is equal to radians to pi. So you could just plug in your angle here for degrees or your angle here for radians and solve for the other one. And we're going to do that here in just a second. All right, example 5. Convert the following from radians to degrees. So if we've got radians, 7 pi over 6, I'm going to take 7 pi over 6 and multiply by 180 divided by pi. And this is how I always do it. I'm going to take 3 and multiply it by 180 over pi. Negative 2 pi over 3 times 180 over pi. And then you multiply through or reduce and then multiply. I'm going to reduce first, get rid of my pi's. I know 6 goes into 180 30 times. And I just multiply 7 times 30, which is 210 degrees. For the next one, it's 3 times 180 over pi. So that's just going to be what? I'm going to have to use a calculator for that, or I would just multiply 3 times 180. I think I just used the decimal in class. It doesn't matter either way. 3 times 180 is 540. So it's either 540 over pi or relatively equivalent, not exactly, over there's pi. And that is 171.89. 171.89. All right, the last one, negative 2 pi over 3 times 180 over pi. My pi is reduced. 3 goes into 180 60 times. So that's negative 2 times 60 is negative 120 degrees. So that one would be going, and I forgot my degrees here as well. You have to divide this. You can't leave this over pi. For this one, you're going to want to divide this. I just kind of wanted to go back and say that. Convert the following from degrees to radians. All right, degree, we got 35 degrees, 105, and negative 245. To convert from degrees to radians, we multiply by pi over 180. So 35 times pi over 180. And what you do here is you reduce, because this is going to be over 1. You get 35 pi over 180, and then this reduces to 7 pi over 36, because you divide them both by 5. And so this is 7 pi over 36. All right, to convert 105, I'm going to multiply by pi over 180. Negative 245, the same thing. Pi over 180. All right. This one's going to reduce by 15. So I'm going to divide both of these by 15. And I get 7 for 105. And I get 12 for 180. And I can't forget my pi. All right. Last one, negative 245 pi divided by 180. And these reduce by 5. So that would be negative 49 pi over 36. And those are my radians from degrees. Finding coterminal angles. Coterminal angles, if two angles in standard position have the same terminal side. Okay. That makes sense. So let me show you what they're talking about here. Example 7. Find the least positive angle theta that is coterminal with an angle measuring 800 degrees, where 0 degrees is less than or equal to theta less than 360 degrees. All right. To find this, well, first of all, I want to show you what it is. I don't want to do it with the 800 degrees because that's pretty substantial. I want to do it with one that's a little bit smaller to show you. Let's see here. I'm going to start with taking 800 degrees and dividing it by 360. And I get 360 degrees. I get 2 rotations, 2 point something. I don't care what the something is. What I care about is this 2. All right. Because I can take that 2, and that just tells me that my 800 degree angle is at least going around 2 times. I don't know where the terminal side is, but it's going around at least 2 times. All right. Now I'm going to multiply 2 times 360 and I get 720. I'm going to subtract those 2 numbers and I get 80. So that tells me that my terminal side is going to end right about here. Because I'll show you, if I redrew this and had that same angle, this right here is 80 degrees. This that's drawn is 800 degrees. They share the same terminal side. They both end on the same exact side. All right. And because of that, they are coterminal angles. All right. So our angle that is coterminal with 800 degrees, and we want it to be between 0 and 360, is 80 degrees. It is the coterminal angle to 800. Show the angle with measure negative 45 degrees on a circle and find a positive coterminal angle such that alpha, such that 0 degrees is less than or equal to alpha is less than 360. Okay, so again, now for this one, we're going to go negative 45. Remember, we have to go clockwise to be a negative. So that's negative 45 degrees. I want an angle that's positive. That's what it said, a positive coterminal angle, which means it cannot go the same direction as this one because this one's negative. It needs to go in the counterclockwise direction. And it needs to end on the same terminal side as the negative 45. So it's going to need to go around and end right here. How can we find that coterminal side? If it went all the way around, it would be 360. But this area right here is 45 degrees. So it's going to be 360 minus 45 degrees. And we get what? 315 degrees. So the coterminal angle to negative 45 degrees is 315 degrees. Is that the only one we could have? We could have an infinite number, because we could have one that goes around and around and ends on it. We could have one that goes around as many times as you could possibly do it and ends on the same side. We could have one go the other direction and have a negative, infinite number of, my gosh, coterminal sides. But we wanted to keep it between 0 and 360. So that made it a little bit more contained, a lot more contained. All right, let's talk about beta. Find an angle beta that is coterminal with 19 pi over 4. And we want it between, beta's between 0 and 2 pi. So we know that when we did this, we subtracted the rotations of 360. Now we're going to have to subtract the rotations of what? All the way around is 2 pi. So we're going to have to subtract rotations of 2 pi. There is a shortcut to do this. Okay. I want to show you the basic just because I think that y'all understood it better in class doing this. But because of the fractional challenges, if you can see what I'm doing here, I'm going to start with 19 pi over 4. If I just take that 19 and divide it by 4, I get a 4 point whatever. I don't care. So that tells me that I'm going to take 4 times that 4, and I'm going to get 16. All right, so I'm going to multiply by, it's going to be a 16 pi, and I'm going to have to subtract that, and I get a difference of 3, 19 minus 16 is 3/4 pi. That's one way. I didn't show you this way in class. I like this way. The other way, the way I showed you in class, is to subtract 19 pi from 2 pi. All right. When you do that, remember we have to, I'm sorry, it's 19/4 pi. When we do that, we have to change 2 into a fraction. So that's going to be 19/4 pi minus, well, we have 4 as a denominator, so we need that. And then 2 times 4 is 8. So I would subtracted those and I got 11 pi/4. But we could still subtract more. So then there's 11 pi/4 minus another 2 pi, which was 8/4 pi. 8, 9, 11, so that is 3/4 pi. Pick whichever one you want. If you like this way and you're comfortable with it, great. If not, you can do the division like I showed you and just subtract it to get the original answer. All right, let's talk about arc length. Arc length is notified, little notation of F. It's the side right here, but only between where these rays are. The length of the curve along the arc between for this angle. Radian measure of an angle is the ratio of the length of the arc subtended by the angle to the radius of the circle. All right. So that just tells you what the degrees are or what the radians are. Okay. S is the length of the arc of the circle. R is the radius of the circle. And if it's a unit circle, the radius is always 1. And then there's a central angle theta containing that arc, and it measures this. S, the arc length, divided by the radius in radians. The other way to write it is theta, the angle, is equal to the arc length divided by the radius. Now in class, I also showed you a couple more that the arc length can be solved by the radius times theta times the angle. It's just multiplication, so I'm just multiply both sides by r. The other way to just algebraically change it is to solve for the radius, if you're looking for it, and it is just the arc length divided by theta. Okay, in a circle of radius 1, that's the one I was just talking about, the radian measure corresponds to the length of the arc. So if this radius was 1, then that means our arc length is also going to be 1. Okay, it corresponds, the radian measure corresponds to the length of the arc. All right, example 2, find the length, and that's for pi. That's going to be, I'm sorry, that's for radians, because you've got each radian measure for an arc length is the radius 1. Sorry, hopefully I said that right. Find the length of the arc of a circle of radius 2 meters subtended by a central angle of 0.25 radian. Note the units in the problem. So we're going to use one of our equations here to solve this. They're giving us, they want us to find the length of the arc of the circle, and that is S. So I'm going to use S is equal to R times my angle. My radius is 2 meters, so 2 meters. And my theta is 0.25. That's radians. So 2 times 0.25 is 0.5. So our arc length is half of a meter. That's how long our arc is from here to here, given a radius of 1, I'm sorry, given us a radius of 2 and an angle of 0.25. So it's half a meter. All right, that is it for 7.1. I will see y'all back at 7.2. Let me know what questions you have, please.